Hi everyone, this is Alex, and this will be a quick introduction to block diagrams, and maybe you don't have enough blocks in your block diagram. So we have a situation where we might have an Arduino, we want to drive an LED with it, and we could say, okay, we just take our Arduino and connect it to our LED, which if we're using a small LED, like one of these right here, that are typically tens of milliwatts, that's all good, because the outputs from the Arduino can provide enough voltage and current to turn one of these on. Like if that was a red LED, it might require about 2 volts across its terminals and about 20 milliamps of current. And if we want to verify if the Arduino can do this, first we look at the voltage, and we know that the output voltage of a 5 volt Arduino is going to be 5 volts when we go to digital high. So the 2 volts, or you could say the 5 volts is greater than the 2 volts, so that means that indeed we could turn this on. In fact, we could put 2 of them on, like we could have 2 of them in series. Like if this is the symbol for the LED, a little triangle arrow with the photons coming out of the side, that's what the little arrows represent. So if we need 2 volts across each of these in order to get it to work, we know that when things are in series, the voltage sums, so that means that we'd need 4 volts total. If we looked at these 2 pins right there to drive these, because we're going to have 2 volts dropped across that one and 2 across there. So everything is good provided that the current isn't too high. And it turns out that Arduino can typically put out between about 20 to 30 milliamps from each of the digital pins. And so there are about 12 pins on there. The deal is though that it can't do that for all of the pins. Like you can't have something connected to each pin that's drawing 20 or 30 milliamps. The Arduino will start to reset and do weird things. And so, we couldn't put 10 of these LEDs on there and run it at full tilt. We'd probably start to get some trouble. Or maybe it would work sometimes. In other words, it's just not a good idea if we're really looking for reliability. So now let's look at a larger LED. So I have this 10 watt LED right here. And so it's claiming VF is what they call the forward voltage for an LED. And it says it's 6 to 7 volts for the red, the R, 9 to 11 volts for the green and the blue. And then it says the forward current is 300 milliamps to 350 milliamps. So now if we go back to our circuit over here, instead of having a 2 volt requirement and a 20 milliamp requirement to drive our one LED, we need at least, let's say, 6 volts for the red LED. And so now 5 is less than 6, so the 5 volts that our Arduino can provide is just not going to be enough to turn this LED on. If we look really closely at this package, you can see there's an array of 9 LEDs in there, and they pulled a clever trick. They put 3 of each color in series, and that's why the VF is so high for this. It's not that they have a special red LED. They have 3 of them in series. And if we go back to the little picture I just erased, if we put 3 red LEDs in series that each drop 2 volts, 2 plus 2 plus 2 equals 6. So that's where we get our 6 volts from. Now notice the current's much higher. So the current of our little garden value, or garden variety, they call it LED right here, might be peak 100 milliamps. That's kind of pushing it to the limit. It's safer and it'll last almost indefinitely if you put 20 or 30 milliamps through it. Where this one says 350. So the big difference is you'll notice that this is mounted on a large heat sink. So you can get the heat out of there. Whereas with this one, the only heat sinking you really have is through the metal pins, like the current or the heat conduction out of the circuit through the pins. Whereas the big heavy duty one's designed to be mounted against a piece of aluminum or copper or something that can draw the heat out of it efficiently. And so now if we go back to our Arduino deal around here, well, we know we automatically lose because we can't provide 6 volts directly out of our Arduino, and there's no way we can get 300 milliamps. So this isn't going to work. If we look at the blue and the red, the blue and the green, we're in the same situation, 9 to 11 volts. It's just not going to work. So what do? Are we stuck? Can we just not use an Arduino? Do we need an amplifier or something? So it turns out that we need to add another box in our block diagram. So we need to have some kind of switching over there. And that's going to require an external power source. Like here we kind of implied that the Arduino was getting power from somewhere, some electrical power, some energy, some kind of battery. So realistically there is an arrow going down there. So now we have another arrow going to our switch right there. And what the switch does is it takes a signal, an information input from the Arduino. The Arduino tells the switch to turn on or off, to turn the LEDs on. So what we can do now is, say if we went back to our red stack of LEDs, we'll just draw all 3 of them just for clarity. So we have our 3 LEDs there, and now we can drive them with our switch. And now we're starting to cross over from block diagram to schematic a little bit. So now I could do that. And so now I added some wires here. And we know that electrical circuits need to close a loop. You need to complete a loop for the current to flow and this kind of stuff. And I just did that here. I'm pretending that these are positive outputs from batteries or whatever. And then this is the ground or the negative input. So you could see that I have 2 loops there. So the Arduino is getting power from the energy source and it's going back to the ground. And then the switch is getting power from the energy source. And if the Arduino tells the switch to turn on, it turns on. Current goes through the LEDs. Photons come out. It gets nice and bright. And then the current goes back into the energy source. So that's what we want to do. Now, there are different types of switches. So the most common ones that you're going to probably use are Mosfets or transistors. And you might say, okay, that's what a MOSFET or a transistor looks like. It turns out all 3 of these are different devices. This is called a tip 31. You probably can't even see it because of the lighting in here. And if you kind of look at it at an angle, you might be able to see that writing on there. Tip 31 is a bipolar transistor. Those aren't great for Arduino, so we're not going to use it. This is a tip 32. That's a negative version, a PNP transistor. Don't want to use that. And this is a, see, it's like P60 something. I can't even read it right now, the light's not good enough. But I know this is a MOSFET because I took it out of the MOSFET box. But the important thing to do is to make sure you read the numbers, because even if something is in the box, I'll bring the light in, well, a little bit there. Yeah, we still can't see it with the camera light, but I could see it, and it says P30 NQELE. I can look up that data sheet and make sure that this is actually a MOSFET. And when I look up the data sheet, I'll also get instructions on the pins, because these pins have to be connected to the circuit in a certain way, which we're not going to get in this video. I just want to tell you that. So one option here is called a MOSFET, and we'll have some videos that show you how to implement that. So the other way to do it, the more classical way, are with relays, and this right here is actually a shield of 4 relays. So each of these boxes is a relay. And the shield, this is cool because it actually can go on top of the Arduino and plug into it. It's kind of like an expansion port. So now, you know, I could control the relays with the Arduino, which it's connected to, and then bigger wires connect to these green terminal blocks over here, and those represent, you know, these connections. So there's a few final things to note. That, so we looked at the current draw on this, and it's high, you know, relative to the Arduino. So 300 to 350 milliamps. So the Arduino might be taking in 30 milliamps, and that means we could use thin wires. Like we could use these little breadboard jumper wires to connect our Arduino to the power supply. So if we're drawing 300 milliamps or 350 milliamps out of our power supply in this branch, we need heavier wires. So sometimes if I'm drawing a schematic diagram like this, I'll just bold my wires in there, because then when I go to build it, or if someone else is building it for me, then, you know, I'll tell them like, okay, the thick wires means a heavier gauge, and I might specify like this should be like, you know, 20 gauge wire or 18 gauge wire, and then this right here could be like 26 gauge wire, so smaller wire, because the Arduino doesn't draw a lot of power, but the switch needs to draw a lot of power or current, depending on how you're doing the math, in order to get the current successfully and efficiently out of the energy source through the switch into the circuit. So that's an important thing. So one last thing that I didn't mention, and you know, we came up before, that if we have 2 volts across each of these, so we need at least 6 volts at our switch output right here. In other words, when it turns on, we need to have 6 volts here relative to this point, which is our ground. So that means that we need to make sure that our energy source has a high enough voltage. So this is right here is implying that we need to be at least 6 volts output on our energy source, maybe higher, depending on how hard we want to drive these LEDs. So, you know, now if I look at it, okay, I got to specify some things right here. So say if we went with a 6 volt power supply, you know, we know that we're going to probably need about 350 milliamps plus the 30 milliamps. So now we're up to, you know, back at, you know, 380 milliamps. Maybe we'll up that to say 500 milliamps to be safe. So we need a power supply that's capable, you know, of continuously running 6 volts at 500 milliamps in order to make this work, because these currents sum. So the other thing we got to keep in mind is that the Arduino will die if you apply anything greater than 5 volts to its 5 volt or 3 volt inputs. So there's a pin on the Arduino called VIN, and you need to connect anything that is above 5 volts to the VIN pin, otherwise you'll burn it out. So the other, if we look at the Arduino right here, there are two ways to access that VIN pin. You can either use this power connector port right here, and you could plug in a power supply or something to it, or there's actually a VIN pin right on the circuit board that you can plug into. So the thing that you don't want to do is you don't want to run the VIN from your energy source into here and then have a wire coming out of the VIN here on the board going to your Mosfet, because there's quite a bit of internal resistance inside the Arduino. So that would be kind of like thinning down this wire to the point where you're causing resistance. So you need to use big wires basically in these circuits.